All right, so our first, and I believe only example of this normal approximation to the binomial is here. So if we read through this, we see that we're talking about a jury pool for an upcoming murder trial. This pool contains the names of 100,000 individuals from the population. The percent of available jurors on the population list who are Hispanic is 40%. Suppose we take a random sample of 300. Whenever we're dealing with these binomial problems, we're always going to have our n, our number of trials. So in this case, we sampled 300. And we're going to have our p, our probability of success, the two pieces we need for a binomial. So in this case, our p is 40%. And x is equal to the number of Hispanics selected to be jurors. So this is exactly what we mean when we talk about a binomial. We're counting up the number of people who are Hispanic from the 300. So this is exactly a binomial. We could say x follows a binomial with our n and our p. Now it asks us, what are the mean and standard deviations for the number of Hispanics? This is asking us for a mean and a standard deviation from a binomial distribution. So if you go to your formula sheet, under binomial, which we know we're dealing with because we have that n and p and we're counting up a number of things, we have a mean and a standard deviation. So this is the two formulas that we're just going to use on the page, np and the square root of npq. So our mean is np, standard deviation is the square root of npq. Go ahead and do this. And this one I don't know off the top of my head. It appears that this is 8.4853. So the correct answer here, 120 and 8.49. All right, so that's our mean and standard deviation. Now, the first question you should ask yourself before you do this is, am I allowed to do it? Because a lot of times students will use this when it's not allowed. So in order to do this, we have to check the rule of thumb. Is our n sufficiently large? Now, 300 is most likely large enough, but we got to check just in case. So our NP we already have is 120. NQ is just 300 times our probability of failure, which is 60%. That's the 180. So if 120 people on our pool are Hispanic, then 180 will not be Hispanic. Both of these are way bigger than 10, so we have our rule of thumb. We're going to be able to use the normal approximation. So now that we have all this information, it says, let's find the probability that 110 or fewer Hispanics will be selected using both the binomial and the normal approximation. So first we're going to do this with the binomial. Because truly, this is a binomial. When we use the normal, we're approximating. We're going to get something that's an estimate. So with the binomial, well, we're looking for the probability that our number of people on the jury pool who are Hispanic is less than or equal to 110. You could also do your little list. This list really proves the reason, how many people were pulling? 300? The reason why this normal approximation exists. Back in the day, people had to use that formula that we talked about, the n choose k, p to the k, q to the n minus k. And if you had to do that formula for every one of these, you would have to do the formula for all of this. You would have to use that formula 111 times, which is nonsense. That would be horrible. In this day and age, now we have these little tiny calculators that are able to do this for 20 bucks, but back in the day, this would not have been feasible. So if we want to do this, this is actually the perfect setup for our Binomcdf. So we would just do this as Binomcdf. We started at 0 and we went up and included 110. So our n is still 300, our p is still 0.4, and the number we want to go up to is 110. So I'll bring up my little calculator and try this out. So, come on, you know you want to turn on. All right. Binomcdf, 300, 0.4, 110. And if you actually type this in on your calculator at home, you'll notice that your calculator actually lags for a second. So 0.1312, because it's adding up all of that stuff and it takes a little bit of time. So this is not something that was possible years ago. So now it's possible and way easier. So that's the binomial version of this. The normal approximation version of this says, well, I don't like that doesn't. We actually know that this almost follows a normal distribution, right? With our mean at 120. And we know that we're looking for 110 or fewer. So we could just use the area under the normal curve to approximate or guess at what this probability is. And how do we find areas under the normal curve? Well, we use Normalcdf. Our lower bound, our upper bound, our mean, and that standard deviation that we had from before. I'm going to just use the rounded version that they had. So again, I can bring up my calculator, and this time instead of doing Binomial I'm doing Normalcdf. Negative crap ton of 9s, 110, 120, comma 120, comma 8.49. And now we get out this value. 0.1194. And some of this is due to my rounding on this standard deviation, rounding it to 2 decimal places, especially when this 5, rounding it up to a 9 is a pretty drastic thing. So you can actually see I'll do a lot better with this value if I write in the real standard deviation, or a couple more decimal points of it at least. Now we're at actually got one worse, 1.93. I've never done that before. I thought it would get better. So, but this is pretty far from that. We have a 13% to a 12%. I mean, it's an estimate, and that's what this is, a normal approximation. And part of the reason for this estimate or this problem is if you look back at our StatCrunch examples, right? There were nice big whole number values. In fact, let's go back and do this question in StatCrunch. In this particular case, we weren't rolling a die, but same kind of idea. We were looking at a probability of success of 0.4, right? That was what we were looking at. And we were taking a number of coins, but in this case, really people, and we had 300 of them. So 300 people with a probability of success of 0.4. We wanted to know what's the probability we get a number that is less than or equal to 110. Let's see what this looks like. So we're flipping 300 coins, which are people, with a probability of heads or being Hispanic of 0.4. So if we did this one time, we get out 114. We expected around 120, so reasonable. We could go ahead and do this 1,000 times and 1,000 more times. And you can see what's happening in our distribution here. We can also see the proportion based on the simulation is actually pretty dang close to what we expected. So our value from our notes was 0.1312, and StatCrunch is saying it's 0.1314. So really dang close. We're only off in the 10,000s place. In fact, the more runs we take, the closer and closer this should get. It's making me a liar, but it should get closer and closer. But here's the issue. And the reason why doing a normal on top of this is a problem. If you just put a normal on top of this, we use 110, and we pretend in a normal distribution that the probability that x is less than or equal to 110 is the exact same thing as the probability that x is less than 110. Because when we do or don't include that 110, all we're talking about is the area of a line, because we're looking at the area under this curve, right? Versus a binomial where we have these numbers to add together. So here, when we're looking at area under a curve, the equal sign doesn't matter. But it really matters in a binomial when we have a discrete probability. So the way to fix this is called a continuity correction. And that's what one of the questions in the homework has you do. So what we want to do is we want to say, okay, well, I really want to include this 110. I don't want to not include it, which is what's happening now. So how do I say include 110? Well, the fix for this, I'm going to change the color so we have a different color. The fix for this is to say, well, let me come a little bit past 110. In fact, let me come right between 110 and the next number of 111. Let me come to 110.5. And that way, when I do what's to the left of 110.5, I'm going to make sure I include all of 110 by including that half. So that's what we do in order to do the continuity correction, is you just sort of look at our drawing and say, okay, if I want to include 110, I need to go to 110.5. So in our normal distribution here, this is going to be the same as doing 110.5. Now, if I had had an original question that said less than 110, fewer than 110 without the equals, then I would have been looking at the probability that x is less than 109.5, because 110 would not be included in, to say don't include it, I would have gone 0.5 the other way. So you're just going to adjust by either adding or subtracting 0.5 to your number, and whichever way makes sense that you either include or don't include the point that you want to. So let's see this in our problem. So we're going to try out, for this example, let's just see with the continuity correction. So with the continuity correction, now we're doing normal CDF, but we want it to start not at 110, right, but at 110.5. That way we are definitely including the 110. Like it said, we want to include it. So we will use still negative crap ton of 9s, 110.5, 120, and 8.49. So now, oops, come on, you know you want to move. When I bring this up, I'm just going to do second enter, and I'm going to go ahead and insert 0.5. Now we get out a probability of 0.1314. So 0.1314, which is so much closer to our real probability. So the continuity correction makes a big difference. That being said, I am not going to make you do a continuity correction on the test. On the test, you are able to just go ahead. If I say use the normal approximation, use whatever value is there, and don't worry about whether we include it or don't include it, and whether to go 0.5 or above or below. I mean, if you want to show off, you can use the continuity correction, but it is absolutely not required.